Welcome back to Scaling Theory. My guest today is Sara Hooker, Vice President of Research at Cohere, where she leads Cohere for AI, a non-profit research lab that seeks to solve complex machine learning problems with researchers from over 100 countries. Sara is the author of numerous research papers, some of which focus specifically on scaling theory in AI. She has been listed as one of AI's top 13 innovators by Fortune. In our conversation, we first delve into the scaling laws behind foundation models. We explore what powers the scaling of AI systems and the limits to scaling laws. We then move on to discussing openness in AI, Cohere's business strategy, the power of ecosystems, the importance of building multilingual LLMs, and the recent change in terms of access to data in the space. I hope you enjoy our conversation. Okay, so let's talk about scaling and the scaling laws in AI. Your latest working paper, entitled "On the Limitations of Compute Thresholds as a Governance Strategy," is absolutely packed with fundamentals ideas on the topic, which explains why I'm so excited to talk to you right now. You do explain in the paper that models running at the same compute capacity today as a year ago may perform better, and we also observe that smaller models can outperform larger models, and you give a couple examples, one being that IA-23 with only quote-unquote 8 billion parameters is outdoing Bloom with 176 billion parameters, which means that it only has 4.5% of those parameters. So clearly it says that scaling compute capacity does not necessarily scale performance. So please tell us about the relationship between compute and performance. And I guess a way of asking the question is there no scaling law at play, or is there a scaling law but less linear than we thought?
Yeah, so this is fantastic, and it's lovely to be here. I think some of these topics in some way touch so many aspects. It's both how we think about these models, but also, what leads to breakthroughs, which is really interesting. And the first question gets to the heart of this, because in some ways it's a question about how we've spent the last 2 decades and, have we spent it well? There's two things happening. So one is, in our field as a whole, as we've built these models, there's been the wide perception that scale more than anything has contributed to progress. And so that's been, if you can think about one characteristic that has defined how we've made progress on these problems, it's bigger is better. Throw more and more compute at the problem. But that doesn't really explain things like the IA-8B, which is, I agree, it's very funny how we've become accustomed to think of 8 billion parameters as small, but this is a reality. It still fits on a single device, so it's considered very small. How on earth, if you believe that bigger is better, do you also reconcile that an 8 billion parameter can handily beat 176 billion parameters? So it's very clear that compute is not everything. I think your question gets to the heart of it. Am I saying, and this is really a question, is this paper saying ignore compute? Is it saying that there's no scaling aspect, or is it saying that it's not a one-to-one? You don't just exchange one compute unit for, equivalent or predictable bump in performance. I think what I'm saying is it's that we don't actually know what we get when we buy compute. It's kind of like going into a fortune teller's house, and you kind of pay for your fortune and you expect some beneficial return, but it's kind of the pick of the day. And so we know that compute in general, if you spend more money on compute, you see gains. But what that doesn't explain is how you can compensate for compute with optimization. And what that means is that there's been very profound optimization choices which have bended the need for compute so dramatically and so pronounced that we now have extremely small models relative to our biggest models, and that are both very performant and increasingly very risky. So it's this combination.
And well, actually, I think if you go to a fortune teller, you are expecting that person to tell you that you do well. right? That you're going
Yeah.
to be the best person ever. And I'm pretty sure that those companies selling you compute are probably selling you the same story. That the
Yeah.
more compute, the better. I would love to be in a room when you do negotiate those deals. But
Yeah.
something else that relates to scale is the quality of the data. And you also tackle that in the working paper, and you show and explain how improving the quality of the data that you have for the training can reduce the reliance on compute. And so that investing in better data may actually mitigate the need for more parameters and reduce the training time. How come?
Yes. And this is fun because this is where this story begins about what bends the rules of compute. And data is very interesting because we've had almost a pendulum swing. So when 2012, when deep neural networks were a breakthrough, in some people's mind, it was almost evidence that all that time in the early 2000s that people spent feature engineering and doing very specific ways of learning features, that it didn't matter, that you should trust the model to learn everything and you should abstract away the data pipeline. In fact, I think a lot of grumpy debates between computer scientists, researchers, was some people cared about data and they said, no, you have to care about the data. And a lot of people said, no, the whole point is to have a general purpose model. You shouldn't think at all about the data. What's so interesting is now we have another pendulum swing because it's very clear data matters considerably and a lot. And what matters is the following, is that if you think about it, we've trained these models on the internet, like large, vast amounts of data. But where we want them to perform is we want them to perform on very different things from the internet. We want like very high quality conversational, we want retrieval, we want all these things. And so in many ways, we spend a lot of time trying to move away from the data we train on. So it makes sense that when you invest more in data quality, you can get away with much less compute because we're spending so much about compute trying to learn, but then forget parts of what we learned. So what do I mean by this data bends the laws? Quite simply, it has been shown in the last 5 years, actually a lot of the work from my lab has looked at this, which is if you invest in high quality data, you can get away with less compute, less training time, and you have more performative models. And what this means is kind of profound because it means that you can't just get away with thinking about the size of the model if you think about performance. From a safety perspective, it's even more detailed because let's say you care about something like biorisk. If a model is only trained on biodata, or if it's trained on very high quality biodata, but a small percentage of it, that model is still likely to be more performant in generating, for example, novel bio combinations than a large model. And so this is very important because it means that when we think about risk, it's not just the model, which is what most of these approaches are centered on. It's about the combination.
Yeah. And something we won't discuss today, but by any means, if you're listening to us and have 20 minutes just to get a gist of what's there, you do have a working paper on biases in data, which I think is also making a very important point. So I won't get into it because otherwise we may be tempted to talk about it. So let's stay on the scaling laws. In that working paper still, you do explain that optimization breakthroughs can offset the need for compute. Now, I'm wondering how this is playing out in practice, and this is where your kind of double hats, researcher and also being in the industry, may provide us with an answer. So let me explain what I mean by that. What I mean is that it seems to me that so far many companies, they seem to be optimizing their models while also scaling compute. So is this the approach that you have taken at Cohere? Have you reduced computing costs over time because of those breakthroughs, or have you invested more in compute with those breakthroughs in order to achieve better models?
Yeah, and maybe this is interesting. There's a few directions we can go on this question. Maybe to give an example what I mean by optimization breakthroughs there, just so people can understand. When ChatGPT was released, a lot of the energy around these models, immediately there was a groundswell of excitement because of the fluidity of responses, by the way that the generative technology connected with how we communicate as humans. In many ways, a lot of the key ingredients that led to that and that have led to, large language models like ChatGPT, like Cohere's models, like Claude, a lot of the ingredients are few. So before ChatGPT, a lot of it was scale. It was like pre-training at scale. It was expanding the coverage of data, particularly large-scale internet data. But that breakthrough happened because of an optimization change more than anything. So what distinguishes ChatGPT from previous models was what I think of as like the gold dust that we apply on top of pre-training. And all it is we call it instruction fine-tuning and alignment, but all it is really restructuring the data. So for instruction fine-tuning, you just change it into, it's to induce these good instruction following properties. You change it into a question answer. Why was this profound? Firstly, it's very cheap in terms of compute. You spend many, many weeks on pre-training massive models. Spend a tiny fraction of that on your fine-tuning. So you need far less data. So for example, Alpaca was one of the most widely used open source fine-tuning data sets, so we can talk about that. It's only 50K, but it's high quality, it's distilled. And this is a smidge, it's a drop in the ocean compared to all the compute we spend on pre-training. This is the challenge that will be faced if you rely just on a measure of compute, because optimization, what we're really talking about is a change of the rate of exchange of compute for performance, a dramatically better exchange rate. So the compute you spend on something like instruction fine-tuning or alignment or best of end sampling or chain of thought, and I'm listing all these things, but feel free to read the essay to dig in. But the rate of exchange there is incredibly high. You get a lot of bang for your buck. And what this really means is that it's worth spending time there. So that's why we see so much work on how do you get the best alignment. We really recently released some of the ongoing work that we have with the wider ecosystem of how we do multilingual alignment. When you have many languages, you're trying to align much better. But to your question, what happens when you both do these optimization changes and you also scale compute? It is interesting. It depends. It depends how saturated your task is, and it depends also on the limits of transformers. But basically, for a given level of performance, and you'll see that most models that have been released have very good performance across many different tasks, you're always going to want to try and bend at this point, because at this point, we're kind of in the feasible deployment era. So we can build the biggest models for like our kind of pursuit of what the biggest models would give us. But in terms of making those accessible to the world, reality is it is incredibly difficult to deploy extremely large models. And so regardless, you're always going to bend. You want to bend the rate of return. And a lot of what my lab spends time on is efficiency at scale. And so for me, the primary question is, how can we do more with less?
So as you just explained, it changes the relationship between, or at least what you can do with compute and the need and where you may want to allocate that. And as you wrote in that paper, the scaling laws
it's saying
we thought
that
maybe
more
will be
than anything.
valuable
we've talked about a few
decades to
ingredients
come,
now. We've talked
the
about
ones that
scale,
we came up with before
data,
2012 actually don't hold after the advent of convolutional neural networks, which fundamentally change the relationship again between performance
what types of
and
solutions
compute.
you can get
So please elaborate on
it's
this.
interesting because what it means is that it fundamentally unlocks new search spaces. If you have a new architecture that's really powerful, for I in the paper it's very clear no scaling laws before 2012 will have held, because convolutional neural networks just fundamentally change what was possible, what types of search spaces you could get to. The same is true. No scaling laws hold from before 2017. You see these, typically people do piecemeal scaling laws and they have different ones for transformers because, again, the architecture fundamentally changed the scaling properties. And what does this mean? Like, why should we care about scaling laws, and why should we care that we can't extrapolate beyond architectures? The difficulty is typically we use scaling laws to understand how our models can be expected to perform, in future levels of compute. And so given how radically these laws can be bended by new introduction of technology, we should use them with a healthy dose of humility about their ability to correctly predict. And I think this is the main thing, is that there are just clear cliffs to their ability to perform and extrapolate in a meaningful way.
Yeah, so they are valid, but given the technology that is available today, right, and may prove less valid over time.
Yeah, and I'll say two things. One is that scaling laws, there's two realms of questions which are interesting. Scaling laws have been shown to be valid within a given architecture for predicting the loss. So as you scale, what's the loss? They've been shown to be much less good at predicting behavior characteristics, like downstream metrics. In fact, most research that has looked at whether they're able to predict downstream metrics has shown murky at best, inconsistent, the results are not there. What does this mean? What scaling laws are very good at, why I always say, researchers should use them on planning your next training run, right? So you're probably within a regime where you're using the same architecture. You're trying to understand, how should I change my data relative to my capacity? And you're typically looking at loss because you're doing pre-training. The difficulty is policymakers are trying to use scaling laws in a totally different way. They're trying to predict out a much larger time horizon. And they, for their inputs, for their decision-making, it's not loss that's of interest, it's downstream behavior. And this is where our scaling laws are most fractured. And that's the real challenge.
Yeah. And so I want to talk about that because indeed, the policymakers, they always want to be quote unquote future-proof, but often what you see is that the idea will be to come up with a regulation that is so good in 2024, you won't need to adapt it in the future, as opposed to making it future-proof in a sense that it can adapt. And so that brings me to what you call the scaling policies. In the Biden executive order and the EU AI Act, we have seen already that a temptation to impose specific provisions on the models trained using a quantity of compute that is greater to, in the case of the US, 10 to the power of 26 operations, and in the case of the EU, 10 to the power of 25. Now, in the EU, this currently covers about 4 foundation models. And we see that in China, California, and other countries, there is a temptation to implement a similar approach. So with advances in performance and changes in architecture, which of course by nature is almost impossible to predict, do you think it is possible that those levels, those thresholds won't even be valid, meaning that all the models will be above, or actually none will be above because, as you just explained, a new architecture may change the need for compute, and therefore it may be that 10 to the power of 24 is enough in a couple of years. What's your take on that?
Yeah, I mean, I think that you answered it in a way. I think that you pointed out two things, right? A new architecture can completely throw up in the air any compute threshold that's arrived at. But maybe we don't have to look at that scenario because, you can never predict when breakthroughs will happen. But maybe we can look at the more reasonable one, which is just that the relationship with compute is changing very quickly. And it's very hard to predict a single number that will define an inflection point. So even in this more moderate scenario, we already see that there's not clear evidence that this is going to be a number that won't have to be revisited constantly. So one example is this. You're pointing out that the AI Act, there's already multiple models that fulfill that criteria. In the short to medium term, there's likely to be more scaling, especially with multimodal. Typically, when researchers don't know what to do, we just throw compute at the problem. So with multimodal, we'll see more. So there'll be more models that make it up, because especially the EU AI Act is at a lower threshold. So it's at 10 to the 25. In the US, we see this 10 to the 26 number. But you can also see the US has already made provisions for things like biological thresholds. These are specific to biology models. We can talk about what that means, but that's set much lower, and several models have already surpassed that as well. So what does this mean? The models that have surpassed the ones to date don't have a decidedly different risk profile. I think there's consensus that maybe the numbers were set not incorrectly, but the rationale is not transparent or justified. And it seems in practice, the models that are fulfilling these thresholds don't feel dramatically different in risk from many of the ones that are deployed in the wild. And this is the difficulty, because if you hinge on a certain number, you are putting a lot of pressure on that number to be robust to not just, the current landscape and predictions, but as exactly you were saying, what happens over the next few years. And I suspect many of the countries or, governance structures that have embarked on this are going to have to create clear mechanisms to constantly adjust, which has its own technical overhead, because then you need consensus and you need some mechanism to make sure it doesn't become sterile as a number or decorative.
What's quite interesting, actually, is that in the EU AI Act, so there are basically two approaches. One that is risk-based, and it looks at, pretty much any use of AI, if it's considered high risk, depending on where it's deployed. And there it says that it's technologically neutral in a sense that it applies the same to every AI system, regardless of how they function, which to me doesn't make any sense, because it may be that certain ways of building the AI are more risky in nature than others. And when it comes to those general purpose AI models, then it has, again, this kind of, numbers that fall from the sky. And we just hope that it will make sense in the future. But regardless of the training and the architecture, as long as you are above the number, you will have to comply with the exact same provisions. I understand why, for the sake of simplicity, you may want to go this way, but it also has to make sense. Now, if we take a step back on those scaling laws, something we haven't discussed yet, because we very much talked about software, is the relationship between that and hardware. And you actually coined the term hardware lottery in 2020 in a paper that I adored. And here what you do is that you describe how ideas can succeed because they suit the available software and hardware, and not necessarily because they are superior. Now, it seems to me that pretty much the entire AI ecosystem, in a sense, won the lottery as it benefited from advances in computing power, which enabled the training of those transformer models, which maybe is good. But in a sense, winning the lottery also comes with its own problems, including the fact that it creates path dependency, i.e., it's harder to explore new ways to improve on your AI system if you can just throw money at the problem and keep on improving, at least so far. And as you also explain, in fact, if you want to explore a new way, you will have to construct an AI system that can outperform the fact that the next generation of the AI system to which you can throw a lot of compute will keep on improving indeed. So in a sense, the scaling laws, at least those related to compute, they are a barrier to try to disrupt, because the incentive is lowered because of the fact that you can simply improve the model by throwing more compute. So how do you see this cycle being broken to develop radically new way to train AI models? Do you think it will come from a big tech company? Do you think it will come from an entrepreneur in a garage? Are you trying at Cohere to come up with a totally new way? Or are you kind of stuck in this idea that, well, more compute will make the model better, and you know what? That's what's easier for us to justify.
Yeah. Maybe let's unpack. I think firstly that the hardware lottery was a paper that was very special to write, actually. And you're right. It's this idea that so much we believe in a lot of freedom with ideas, and the idea that we're creating these breakthroughs, but in many ways we're so boxed in already by our choice of hardware and software. So what you're pointing to is the dependence of deep neural networks on GPUs. So this was developed for video games, and it was really a fluke, but also a lot of pretty much a decade of slow adaptation to machine learning workloads that made 2012 possible. We've talked about that dramatic change in scaling law in 2012. That was because of GPUs being applied to the convolutional neural network problem, along with more data. But GPUs were what allowed it to be empirically successful, because you could have deeper and larger networks, and that turned out to be key. Since then, it's almost like we've just bet more and more on GPUs. Like even the latest H100s from NVIDIA were called the Transformer Engine. I mean, this is a nice bit of marketing, but it's really just overfitting more and again to matrix multiplies. So what does that mean? I think it's very hard right now to stray off the beaten path of ideas because, frankly, compute is a very easy formula to justify. So you don't know how much you're going to get in return, but you're going to get something. And so if you're in an industry setting, you say, well, what can I do with 4 months of the year? Well, I can either try and experiment with all these optimization choices, or I can throw compute at the problem and let's see how much we get. This is bad. I think it's bad for like our overall progress because the stickier it is to experiment, the more issues you have with finding new models. And there's severe limitations to our current models. So I'll share a few that are just really fundamental obstacles. One is that our models need global updates, which means we have to update all the weights when we train them. This means they forget as they go. So your model is very likely to not remember old data if you train it with a lot of new data. But also, we have to show all the data to our models, which is nuts because, as humans, we don't look at all data equally. Like, you typically zoom in. You typically are very specific with what you pay attention to, mainly because you have to be. It's forced efficiently. Like, we have log scale vision, so we need a noticeable change to register. We typically only do a forward and backward pass if something changes. These are all hard-coded ways in which we radically reduce the intake of inputs and spend more time. And these are just some limitations, but what is very clear is that the architecture of the future will not be a deep neural network or a transformer. It will have to be something different to overcome these issues. What does that look like? Where will that come from? Frankly, tooling is one of the biggest obstacles. I'll talk about some promising ideas that don't play with tooling right now. One is sparsity. Sparsity is what we actually have. We have pruning in our neural synapses. As you grow up, you typically have a massive restructuring of your brain where some synapses are grown, some are, decay, and it is according to saliency of what's important. When we do sparsity, which is the same, we remove weights, we kind of change the structure of a network. The difficulty is that we still have to use a matrix to store. And so we actually don't gain sparsity. Our hardware, the way it's built, means that we still have to use a full matrix to add a zero to represent the absence of something. So this is a fundamental stumbling block in how our computer science field is developed. That means we can't do things like dynamically grow networks in an efficient way. And that's just one. But yeah, maybe I'll pause there and then go for it to Walt.
Well, let me ask an impossible question.
Yeah.
Just for fun. And also because I'm very interested in the answer. With all of what we discussed so far regarding scaling laws, how good they are, the limitations, if you were asked to come with a general scaling law regarding the growth of foundation models, which element would you include?
Oh, interesting. In what sense? Go for it. What do you mean?
Well, so we mentioned the need for good quality data. So probably there is a relationship between the quality of the data and your ability to scale the quality of the model. Maybe it might be that there are, some sort of tendencies in new architectures coming up. So with your background, which elements would you say are absolutely, and compute, of course, will also play a role as we discussed. So which elements would you include in that definition if, we were trying to come up with a beautiful equation that we could put on the board?
So it depends on the time horizon, because this is kind of like saying, what would you bet is the biggest vector of change? Within the paradigm of transformers, data is going to bend your return the most, because at some point, and what we don't talk about as much, is that all these architectures saturate. Computer vision, convolutional neural networks have saturated. Transformers, what we're doing right now is bending the curve for saturation, but it will saturate. Like, there's a certain search space that an architecture can reach. So by far, if you want to truly transform a scaling law, you have to bet on architectures, but it's one of the most riskiest bets. Not as risky as hardware. Hardware is by far the riskiest, but it's up there. And there's some interesting bets there. We do a lot of work on modular adaptive compute. How do you have pools of models where you route differently? This is much more interesting because you get at specialization, and you can have this idea of like not having a single monolithic model. Adaptive compute is very compelling, but these are all future bets in many ways. Another one is state space models, which doesn't play well with current hardware, but is promising for many reasons. But architecture is your biggest definer of the relationship. Anything around like optimization data is really just bending the rule within an existing rule. It just doesn't change the law itself.
So I need to have a look at whether there are papers out there, and empirical papers especially, documenting how often do we see new architectures coming up, and depending on which variables, right? So this will be interesting to.
And here's the thing, because a lot of people propose new architectures that are kind of not significantly different enough, but there's some that are out there. I think Mixture of Experts, for example, is very novel in the way that it's structured. This is a new architecture.
Yeah.
It's still reusing some of the building blocks, but it's doing it slightly different. And then state space models, very interesting. That's something that doesn't have empirical success yet, but people are excited about because it truly is doing something different. Capstone networks from Geoffrey Hinton, that, hasn't been adopted, but it has at least interesting ideas that are different about the way that the model should learn. And this is fun. It's just that they're very hard to prove empirically successful.
Okay, so that actually makes for a perfect transition to part 2 of our conversation, where I want to talk about openness, right? And so the marketplace of ideas and indeed new architectures being available up for grab. I've mentioned already on the podcast, I'll say it again, that I'm biased. I support open models, mainly because of my antitrust background and the fact that they do alleviate many antitrust concerns and foster competition and innovation by allowing fork, right? So what's interesting with Cohere is that one of your model, Aya, is actually one of the most open models. And actually, with my co-author, Jason Pott, we tested the most commonly used models, and we found that Aya was number 1. And the reason for that is because not only is the model open from a technical perspective, the code, the weight, all that is available, but it's also open on other elements that are not technical, such as not having a strict access rights, such as usage capacity. There is nothing similar. Not having non-competes in terms of what you can do with the models in the terms and conditions, and so on and so forth. And so it follows that Aya is it's more open actually than, for example, Llama 3 and other quote unquote open models. So can you please tell us about what motivated this level of openness?
It felt almost like not just important, but it felt very necessary for Aya. And maybe it's worthwhile talking about what Aya was, because it was in many ways a grumpy model. And what I mean by this, it was a protest against the state of progress for multilingual. So multilingual had always been treated, I think, up until Aya as kind of a side thought. Okay, this is great. If we have people used to call it accidental multilingualism because they didn't know it was in the pre-training data. So then they were like, oh, wow, how lovely that we have this. But it was definitely, English and Chinese were first-class citizen languages because a lot of the technology is developed around them. English first, Chinese first models. And all other languages were really secondary, profoundly so, like sharp cliffs in performance. And the state of research was also often about small steps rather than big leaps in progress. So Aya was an effort that was meant to establish both a new measure of progress as well as connect an ecosystem. And this is the other component, which is that one of the aspects that I'm most proud of in terms of openness is actually not captured in the final artifact, and we don't talk about it as much, which is how the collaboration happens. So I, in particular, was 3,000 people around the world, and it was a community of researchers who worked on this for really a year and a half, building both the extensive collection of data as well as the model. And Aya covers 101 languages. So For me, the why IA should be open was that it's really also a statement about how breakthroughs should happen, as well as, to your point, how we make sure that this accelerates. So since IA, I think we've released more performant versions of IA, but also it's really catalyzed multilingual research, which I think is perhaps one of the most special. We see kind of much more focus on languages and much more realization that this has to be covered as part of state-of-art models.
Yeah, I want to come back to that because I think it's a fundamental point toward the end of the conversation. But Grumpy Models, that will be such a nice title for a paper or even a book. It's yours. All right. So something you've mentioned. Okay, so a couple 100 people working on it for a year and a half. And yet Cohere is a for-profit company. So how does openness align with a business strategy?
Yeah, I think that there's, so Cohere for AI has always been this belief in a hybrid space. And so Cohere has proprietary models. So Command R and R Plus are proprietary. The versions that we've released for open weights, I think, as part of our commitment to safety auditing. But it's a proprietary model. But I think that when you create a hybrid space, especially what Cohere for AI has done, it's this bet that you grow the ecosystem as you grow. And so I think this is crucial for a few different things. Right now, progress is impact. So research questions are closer than ever to real-world impact. And so having this bet, for example, multilingual and accelerating progress in 101 languages, frankly, few of those languages are served because most are not considered commercially viable. They're not considered commercially interesting. But what you learn when you further progress on 101 languages and the sheer enormity of it, because most people can't even name 25 languages. It's very interesting. You can probably list the first 10 very quickly, 15. Yeah. But when you get to 25, it starts to get crazy. It's kind of like building a rocket to the moon. It's the most extreme setting of all these settings. So anything you learn there about optimization, about the implications of how you model better, it transfers to these more particular narrow settings, and you gain such domain expertise because it's the most hard setting to work on it in. So I frankly think of this type of research as crucial, not just for progress overall and building an ecosystem that you connect with and give back to, but also to impact. So whether that's commercial or whether that's also impact in the wider sense of progress in our field. I will also say Cohere for AI is very much a lab in the way that, Brain or early Meta has been a lab, which is that, and Google Brain doesn't exist anymore. It's been folded into DeepMind, but I came from Google Brain. I was at Google Brain for a long time. And then the theory was that when you attract great talent to work on formidable problems, that the breakthroughs that come out of that fuel a lot of discovery. That was true with Transformers, for example. It was true, people forget that Imagen came out of Google, so diffusion models. Many of the breakthroughs came out of places like Google Brain, where there was a bet on talent and also giving this ability to pursue beyond the immediate. And I think this is still crucial.
Yeah. So to give people out there a taste of what's available, some models are quote unquote open, and yet they support only 1, 2, 3 languages. The website is only available in English. The technical documentation is, of course, only available in English, right? So it's hard for people outside of or at least non-native English speakers to access that, which is, of course, something that you addressed with Aya. And yet you mentioned that you are also running a closed model, Common R. And so I found that this dual strategy is quite rare, as most organizations, they tend to choose one side or the other of the openness spectrum. Could you please explain how you are using, on the one hand, Aya, and the other end, Command R, in order to feed each other? Is it that you make the progress that you make for one available for the other, or is it just that the entire team is working on both, and having an open model is actually a way, as you mentioned, to attract some of the talented people because, I don't know, it's more kind of the philosophy in the field. So what's the relationship between those two?
Yeah, I mean, we released the model weights for Aya, so, people do with it as they want. We don't, once we've released it, there's no way we get data or understand how it's used. I think that typically a lot of it comes from being the leaders in multilingual. So when people know that you've done something like Aya, when they need something which is even more powerful for their particular language, they want to use a proprietary model. So there's a very different, very profound difference between everyday use cases of models in terms of researchers making progress, or, developer ecosystems making progress, and businesses who need state-of-art language for their particular use case. Yeah. That being said, I lead our research team. So my focus is on our forward bets. It's on what comes next. But that, of course, when you have something as close as what we do now, where research, directly impacts, this also has, kind of powerful impact. So I think a lot of the things that we learned from Aya, we shared with the world, including, with our own team. So we released an extensive paper. We made the data set available for everyone. But this is the type of traditional bet on the role that research can play in industry. It's unfortunate other labs don't do this anymore. There is a trade-off, right? You give up some degree of control over your ability to not share all details. The reason why Aya was possible because we had built so much trust in the community because we do share details. We did release an extensive paper. And this is a tension. We do that, but we give up some degree of being able to have all those degrees of, kind of all the tricks that you use for optimization for yourself. I think it's unfortunate that we've gone into such a binary world. I also think some breakthroughs like Aya could not have happened in a binary world where you're fully closed. Because especially for multilingual, you have to partner. This is the nature. And that's why Aya became state of art for multilingual, and it's still state of art for multilingual because other organizations don't have the flexibility and setup to engage deeply with researchers or the community. And so we'll always be playing catch up. And so from that sense, you can understand how it's both our commitment to the wider ecosystem, but it's also our strength.
Let me ask actually another question regarding your relationship with the more business side of Cohere. In episode 3 of the podcast with Thomas Wolf from Hugging Face, we discussed how it makes sense for a company such as Meta to try to maybe commoditize their foundation models because it will actually decrease what competitors can generate with those, while also being able to actually deploy the foundation model within an ecosystem that they have already and exist and make money there. Cohere is not vertically integrated. So do you think it makes it harder actually for companies such as Cohere to pursue open source AI? And is it something that you consider when you do it? Do you have which kind of relationship do you have with the business side again of the company? Or are you just focusing on research and whatever comes out of it, the business side would just adapt?
Yeah, I mean, I think when Nick and Aidan first invited me to lead Cohere for AI, I think it was now 2, maybe 3 years ago, which is kind of crazy to think about. They told me we want to start a research arm. And to be honest, my reaction was, you're crazy. Like, this is a lot of work. Do you know what you're doing? Like, what is the goal here? I think the goal is, one is that when you are a frontier AI company, you have to have an investment in what's next. The second was that by doing this as a hybrid lab and being able to engage very, very flexibly across an ecosystem, we knew we were never going to be Google Brain because I was a Google Brain. And, this is a massive research organization. You have 700 people. The goal was always to change not only, the type of research. So our bet was really on this profound research agenda that kind of many people were not looking at. So multilingual, pre-training dynamics, efficiency at scale. but also to change how it's done, to reshape a rubric and to create a new type of lab. And so that's been important. And it's important in terms of how we think is both our impact as well as our strength.
Yeah.
As for foundation models, I think that increasingly, I suspect people will not only care about foundation models, they care about the tools they use it with. This is a reality. I think that most people right now are taking as much a bet on how they're interacting with the model as well as the model itself. And so I think that's increasingly where the focus will go, is that how do you present a model? How do you make it easy to use? And how do you make it actually work for what people want it to work for? And oftentimes, we've had this interesting shift from very specialized to very universal models. And people want universal models, but they also want a model that works for their 3 use cases. And this is where I think it's interesting. And this is where it's less about, a foundation model per se. It's also about adaptability. And so how do you adapt your models cheaply? What are the tools that you give? And this is an area where just releasing a model doesn't get you there. It's kind of a combination of things.
Yeah, indeed. And again, we come back to this idea of the need to get access to maybe specific data to tailor the actual model or fine-tune the model or use other techniques so that it's very much, what people expect it to be. Let me ask a final serious question and then maybe take a couple minutes to ask some more personal questions. We talked about the openness of the space, but of course, it's not just about the openness of the models. It's also about how open the data is. And as a reminder to our listeners, in most countries, and certainly in the EU, you can actually scrape the data for the purpose of training AI, unless the content provider expressly mentioned that data should not be used for this purpose. Now, you just co-authored a paper that came out a couple of days ago on the decline of what you call the AI data common, showing a rise in AI-specific provisions on websites to limit content use. To give some numbers, you find in the study that crawling restrictions increased about in between 26 and 53% in just a year. So in a sense, you highlight that there are trade-offs between intellectual property and openness, as well as intellectual property laws and fairness and competition. Are you in favor of openness also when it comes to data? And what's the limit, if any, that you would put on that?
Yeah, those are various big questions. Maybe I'll share why. So that paper is that by Shane, who's fantastic. Why I thought that paper was important. So maybe that's a good starting point. So that paper is not just about how patterns have changed. It looks at this kind of weird tool we have on the internet. It's called robots.txt. It emerged a few decades ago, and it was never intended for expressing consent. So it's very odd that it's become the primary vehicle along with, terms of use for doing so. What's even odder is that it's not a true vehicle. It's a gentleman's agreement. It's based on the foundation of the internet and this idea that we respect it because that is the ethos of the internet. So when I first embarked on this paper with Shane, one of the reasons I think it's so important we did this work is that there's 2 questions here, right? One is, what are people trying to say with the available tools? They're clearly trying to express that they want to have more control over their data and how it's being used. The other is it being done effectively? And I think robots.txt is actually a very outdated vehicle for this. And it requires that the person specify individually every single aspect, every agent that it doesn't want to crawl. So it requires an exhaustive list. This is a huge burden to put on an end user or domain user. So from that perspective, I think very little can be said definitively historically about data because our copyright laws simply didn't take this into account. So it doesn't really make sense to speak to that. But my goal with this paper was, I do think it is very valid for us to say we want consent to be better represented going forward. Now that there's been change in the usage of data. And that's the main takeaway from that paper, is that I think that if anything, policymakers should pay attention to how do you give people the ability to efficiently and correctly express their intent going forward.
Okay, Let me ask maybe two more personal questions. One that strikes me when I read your publication is that you make references to complex systems and complexity science quite a few times in your publications. I'm wondering if you are using complexity science in your daily work, so when it comes to the more practical side of what you do.
Well, it depends. What do you mean? What aspect?
Well, I guess, are you thinking about how robust a model that you are building might be, or how fragile the ecosystem is when it comes to investment and research, spending resources? Is it something, of course, not, thinking about it like, okay, today on my agenda, 10 to 11, I'm going to think about complexity science, but do you think it infused your approach?
Yeah, in that sense, almost certainly. I mean, a lot of what I think about is, how do we justify what we do? So it's very interesting. Most work, I think our reliance on compute has been a difficulty to justify. So we just know that this is the easiest route, and so we go for it. But forcing justification of why we do things and what we expect, as well as how do we expect our models to perform in the wild, this is one of the most interesting dynamics that exists, right? And so much of my work is at the intersection of, if we make progress on it, it's both theoretically interesting as well as it has real world implications for these models in the wild. Some of the biggest areas of research I do are efficiency, it's robustness, it's understanding really the safety implications of some of these models. And these are all related to complexity and also to, how agents interact. So this is going to be the next frontier when we think about pools of models, how this is going to become even more codified. What is the code of conduct for pools of models and agents who interact?
Yeah. All right. Still trying to understand where you're coming from a little bit more. And this will be my final question. I found on your personal website that you grew up in various countries in Africa, including Mozambique, Lesotho, Swaziland, South Africa, and Kenya, and that your family is still located there. Do you think it has an influence on your work? And is it possible that the fact that AI supported that many languages is actually a reflection of your experience in Africa?
So it's interesting. It's always hard to parse what parts of who you are as a person influence how you think. But I would say more than anything, so my parents moved a lot as I grew up. And so I think in many ways, perhaps what has informed me most is the sense of having different parts of myself that belong to different places in the world. And what that typically informs is a sense that you don't feel very beholden to any particular stance, and it can open up your way of thinking about the world. That being said, I think how it's informed my work the most is that I have a big bet on creating new spaces for research. I really believe that talent is everywhere, and the way that we've created the lab is both hybrid. So we have a huge group of collaborators around the world, but even within our full-time staff, where I have researchers who are in the Netherlands. I have researchers who are in Berlin, in London, here in the US, in California, Toronto. So this was a bet. It's a bet on talent and this ability to find the best around the world. In terms of Aya, I would say that Aya really was from this idea that we can't wait what's most immediately in front of us. And perhaps it was informed in many ways by the sense that I think what's most baffling about this field is it's come from a few groups. And so, we all know what labs those are, and they all recruit from a tiny pool. So it's probably like 5 universities in the US, 2 in the UK, maybe 1 somewhere else. But this is a tiny pool of talent. And so it's a very much an over-indexing of what problems matter to this group. And multilingual isn't one of them. That's why it featured nowhere. So for me, this was a protest. I was a challenge that we can really create new state of art by expanding the view and by taking into account and building a new ecosystem. And I think this lasts way beyond Aya, because once you spend the time building a research community like that, there's many problems that you work on together. And so it's continued. The Aya research ecosystem has been built and continues to go.
Well, thank you so much. By all means, I hope we stay in touch. I found your research truly fascinating, as I tweeted a couple of days ago. Your publications I mentioned in today's episode are amongst the most fascinating I read in recent months, and I really mean that. I promised myself to invite scholars and people and experts with whom I would disagree on the podcast. Today was not the day. But in any case, thank you so very much for everything you've been doing. And to everyone out there, take care of yourself. And if you can, someone else too. Bye-bye.
Yeah, that's lovely. Thank you so much.